All right, in the last video, we talked about hybridization. We looked at one example. We looked at CH4. We said that carbon is made of an S and 3 Ps, and as long as they all are unpaired, which is not the default answer, we get 4 orbitals, which can be visualized as like molecular orbitals. So they shape a little differently, and you can basically get a tetrahedral geometry out of this. Okay, let's try a couple other examples to see how this works, and then we'll expand into new territory here. So if we had something like NH3, if we drew this, we know that it's got essentially this geometry. So experimentally, we know this is the shape. Okay, so it's a variation on a tetrahedral. We have 4 electron groups, which means we need to get 4 groups out of this. Nitrogen, I'm going to stop right, it's 2s and 2p, but I'm going to stop writing the 2's in the front. We just care how many s's and p's there are. So it has an s orbital and 3 p orbitals to work with. Okay, because it would normally be helium 2s2, 2p3. Okay. And what we find is that because we need 4 equivalent groups, we're going to take all 4 of these orbitals. I'm aware there are 5 electrons, but we're combining 4 orbitals to get, 4 atomic orbitals to get 4 hybrid orbitals. Okay. So we get an S and 3 Ps. And we put 5 electrons in it. And we still follow it like we normally do. But now, the way this works is it should sync up to the Lewis structure. This is the lone pair. And these 3 are the single bonds. Right? So that makes sense. We have a paired up one. That's that pair right there. Okay. These 3 are the single bonds because unpaired ones are needed to make bonds. It has to have an unpaired one from one electron and an unpaired from another, and they overlap. And that's how you form the bond. So the idea is it's almost easier to draw the Lewis structure and look backwards down to here to make sure it syncs up. But the hybridization would still be sp3. So honestly, all I'm really looking for on these is this sp3 thing. This is the hybridization of this atom in this molecule. Okay. We need to throw a slight wrench in the works here. We need to talk about what happens if you have multiple bonds. So if you have double bonds, triple bonds, things get a little messy. It's not horrible, it's just a little messy. Okay. And so let's talk about what happens if you have multiple bonds, because that's going to start changing the answers a little bit. So we need to define something called a sigma bond. Any of you in sororities or fraternities probably know that big capital, almost an E looking thing. This is a lowercase sigma, so it looks like this. Okay. These are single bonds, and they overlap end to end, and they're usually made of hybrid orbitals. So for example, if you had 2 carbons, okay, and they were bonded together, the way we would typically visualize it is, we said that if you have all single bonds, you know, you have 1, 2, 3, 4 orbitals, you get sp3, and you're going to end up with this type of shape. Okay. The way we would visualize it is we end up with an orbital like that, and then a little side over here. I'll actually finish them off so they look a little better. And then I guess I'll do the other one in a different color just for contrast. So both of these are hybrid orbitals, but the idea is they overlap end to end. Okay, they're pointing towards each other. The electron density is overlapping. You end up with, I guess I'll keep with the different color thing. You end up with each of them donating 1 electron, and the overlap pairs them up and forms the bond. Not a big deal. Pretty great. Pretty much anytime you have a bond between any 2 atoms, you will have some sort of sigma bond. Okay. Anytime you have double bonds, triple bonds, anything more than 1 bond, you end up with what are called pi bonds. presumably you know what the pi symbol looks like. Okay? These are double or triple bonds. Hold on. Okay. So in the last one I said made of hybrid orbitals. Just check. Okay. Double or triple bonds that overlap side to side. And these are exclusively made of p orbitals. Okay, this is where things are gonna get a little weird looking. So I'm gonna look at a specific molecule and try to draw these orbitals and try to explain what's going on. Okay, so let's look at C2H4. It's a compound called ethylene. It's used to ripen fruit. It naturally is produced by apples more than most fruit, which is why you don't ever put your bananas near your apples in your in your fruit bowl. The apples will produce ethylene and make the bananas go rotten. Okay. What we see is that if you had a carbon, we would expect it to be an S and 3 Ps. I don't know why I drew that so wide, but wow, that is horribly misshapen. Let's try again. S, 3 Ps. Okay. And we expect there to be 4 bonds. You know, like if you draw the Lewis structure, it looks like this. So this carbon has 1, 2, 3, 4. This one has 1, 2, 3, 4. And what we find is that we should expect there to be 4 unpaired electrons. Okay? And what we find is that if you look at this, anytime you have a bond between 2 atoms, it's a sigma bond. So anytime there is a bond between 2 atoms, there is always there's always a sigma bond. You can't have more than one, but you know, it's like between these 2 carbons, there's only 1 sigma bond. If you have double or triple bonds, the first one is a sigma, any additional ones are pi bonds. Okay? And they are made of p orbitals. So what this means for us is before we start combining these to make hybrid orbitals, we need to actually account for the fact that one of these has to be pulled aside and set aside to make a double or triple bond. So if we look at just, the carbons are equivalent, but if we look at just the left one, we have 1, 2, 3 sigma bonds of equivalent types of hybrid orbitals, and we have 1 pi bond. This pi bond has to be made of a p orbital. So one of the p orbitals is already called for, it's already being used. Okay, we just merge whatever's left. So instead of getting sp3, because we're not using all 3 to make hybrid orbitals, we use an s and 2 p's. So what we end up with is 3 equivalent orbitals that are an s and 2 p's, and then we end up with this p orbital. And what we end up with here is this is our 3 sigma bonds, and this is our pi bond. And so this would be true for both carbons, but we're only looking at 1 carbon right now. So we have 1, 2, 3 sigma bonds, and they're all equivalent, and they're each made of an s and 2 p orbitals, because that's what was left. And we have 1 pi bond that has to be made out of a p orbital. Okay? In terms of visualizing what this looks like, I'm going to try my best to draw this. Okay? So carbon, so the C2H4, I'm going to draw this thing with sort of the correct geometry, but I'm going to lay it on its side so we can see these p orbitals better. What we would expect is, I'm actually going to, when I draw hybrid orbitals, the little nub on the back really usually gets ignored, so I'm only going to draw the 1 lobe. Okay? We have a lobe there and a lobe there, and that makes our sigma bond. I'm not going to put the lines in for the electrons, but that makes our sigma bond. Then we also have 1, it's kind of hard to draw wedges and dashes, but we have 1 coming out toward us. It's going to overlap with a hydrogen to form another sigma bond. Do the same thing on this side. And then we have 1 facing away from us with another hydrogen. And that's supposed to be a sigma. Sorry, it's hard to draw. Okay, these are all end to end. They're directly overlapping. We get sigma bonds, okay? And for this carbon, we have 1, 2, 3 equivalent sigma bonds made of 1, 2, 3 hybrid orbitals. Everything, the math all works out. Everything's great. We still haven't accounted for this pi bond, though. Pi bonds are made out of p orbitals. Well, p orbitals go up and down. Okay, I'm intentionally drawing them a different color so we can keep track. This is our p orbital. Okay, so instead of them interacting like this, they're parallel to each other, and they actually kind of like bend over and reach each other to make this work. I typically just get lazy and draw it like this. So what we have is a sigma bond in the middle and the pi bond above and below. This is only one pi bond. Okay. So even though the electron density is above and below, it counts as one pi bond. One thing I will point out is that single bonds can rotate. So what I mean is if you have two things overlapping end to end, they can twist. Okay, they can rotate. Switched pens, sorry. Double and triple bonds cannot because of this pi bond. It's connected like this. To rotate it, you'd literally have to break the bond, and that's not going to happen. Well, it can, but it requires a lot of energy. It's not just going to happen on its own. So double and triple bonds can't rotate. You end up with a more rigid structure. Okay, I do not need you to be able to draw this, but it is important that you understand that this is what it's going to look like. Okay, let's try another example, something with a triple bond. Okay, let's try C2H2. This is acetylene used in blowtorches. The structure would look like this. It's a really simple molecule. It's basically two carbons with a triple bond in the middle, and there happens to be some hydrogens. Okay, so same logic we used on the last problem. Anytime you have two atoms connected together, that's a sigma bond, and these two are connected together. One of those is a sigma bond. You can't have more than one, but you have to have at least one. The additional ones, you're going to end up with one sigma bond, and then there's two more bonds, so you're going to end up with two pi bonds. Okay, so in terms of the hybridization, for carbon, we expect there to be an S and three Ps. Let's see if I can draw this right, unlike the last page. We have 4 bonds, we need 4 unpaired electrons. We are already calling on 2 of these to be pi bonds. We have 2 pi bonds, so we need 2 p orbitals. And this carbon only needs 2 sigma bonds, so we combine what's left. And what we end up with is 2 atomic orbitals going in. One of them is an S and one is a P, so this is just an sp orbital. And then we have 2 p orbitals. And each of them is unpaired, so they can form bonds. And what happens is this forms our 2 sigma bonds. So for this particular carbon on the left, we have 1 sigma bond on the left and 1 sigma bond on the right, and they're both made out of equivalent orbitals. For the p orbitals, this is where we get the 2 pi bonds. Okay, I am going to try to draw this, okay, kind of like I did on the last one. This one's going to be a little messy, sorry. So what we have is 2 carbons. Try to draw them closer because last time it didn't really work out to have them far apart, but that's okay. The geometry here, we'd expect this to all be linear. This is literally what the structure looks like. It's a straight line. So we have an overlap of the atomic orbitals, which I didn't draw big enough. I'll try that again, sorry. Okay, those are the atomic orbitals, and we get a sigma bond right there. We would also have, hybrid orbitals. We'd have another hybrid orbital on the other side connecting to a hydrogen, just like we did in the last picture. But everything is linear in this one because that's what the geometry is. Okay, I'm going to draw one of these sets of pi bonds, because we have 2 of them. I'm going to draw 1 blue and 1 red. The first one's going to look just like the last example, where we have an orbital up above and below. This is what p orbitals look like. They are parallel to each other, and they lean over, and they interact. Okay. You'll note that it's probably not as strong of a bond as the sigma bonds because it's not a great overlap, but it is what it is. Okay, now, p orbitals are all 90 degrees to each other, as we saw, I don't know if I can find my picture, as we saw way back in this video. everything is 90 degrees. So if I draw another set of p orbitals, they have to be 90 degrees to this one. I am going to try to do that. Let's do it this way. So this is coming out towards you at 90-degree angle, like literally straight towards you. And this is going back. And this one is back there, and this one is back here. And then these overlap. I'm kind of trying not to draw it over top of the blue, but whatever. So basically this is one pi bond, and this is another. This is also why we can't have anything more than triple bonds. To have a quadruple bond, we would have to have yet another yet another p orbital perpendicular to both of these that ends up being parallel to each other. This is as good as it gets. So single bond, double bond, and triple bond is as much as you're ever going to get out of this stuff. Okay, so a quick summary. Here's what I'm going to tell you. Anything in the second row, you really don't have to think that hard. So for carbon, nitrogen, and oxygen, okay? If it's all single bonds, it's sp3. If it has one double bond, it's sp2 because one of the p orbitals has been used. So sp3 is as much as we could ever get. One of the p orbitals has to be used for that double bond. If you have one triple bond, it's going to be sp, because two of the p orbitals have been used. If for some reason you end up with two double bonds, it's also sp. I literally count through it using my fingers. Okay, so we have, for anything in the second row, you have an s and three p orbitals to work with. The s orbitals are never going away. If you haven't used any of them, you have an s and three p's to work with. So if you haven't taken any away for p orbitals, or for pi bonds, sp3 is the answer. Every time you make a pi bond, you take away a p orbital. So if you have one double bond, that's one pi bond, so that's one p orbital. You have an s and two p's to work with, and you get sp2. If you have a triple bond, that's two of those gone. You have an s and a p, and two of the p orbitals are used up. If you had a double bond, two double bonds, this could be used for one and this could be used for another, and you get the same answer, sp. So honestly, anything in the second row, carbon, nitrogen, and oxygen, which are most likely targets, or the most likely things that you're going to encounter, especially if you take organic chemistry, you can honestly just memorize this and not really put any thought into it. Okay? We are in the next video going to look at what happens when you violate the octet rule and how complicated this gets. All right, thanks.